record it now. Stop it.
But when you give it to her, she's going to want the least amount of washing possible.
I'll trim it.
I'll trim it.
Oh, thank God.
Aw, how cute.
Make sure that's a recording.
It's not you. Like,
Oh, yeah, we can all
Is
tell
it
the
recording? Oh my gosh. Oh, in October.
No, the short term.
No, here, you back up so I can make sure it's aimed at, like, right there.
Okay.
Hi ho. Hi ho.
Okay, so there was one tiny little thing left in that last set of notes, and I decided that I wanted to get started on oscillations and waves today. I will give you a take-home test on the other material next time, but we need to really kind of cruise through oscillations and waves, and then we can do electrical circuits and we'll be done. So you're all aware of what an oscillation is. We see them all the time. Just pounding on the wall causes the wall to vibrate. Okay? Pounding on lots of things causes some kind of vibration. So an oscillation is a repetitive movement of an object back and forth over the same path. In other words, a vibration. The model of this kind of thing is a mass at the end of a horizontally oriented spring with the mass resting on a frictionless surface that can be displaced, resulting in either a compression or extension of the spring. Okay, so this is the model of an oscillation. This is how we're going to figure out the formulas that we use to analyze this mathematically. Okay? So, and you can see that if I compress the spring and then let it go, it's going to move back and forth. And since there's no energy loss because it's a frictionless surface and there's no air resistance, it'll just sit there and keep going forever. In other words, it's a vibration. But because of the way that we set this up, we can use a lot of things that we already know something about to analyze this kind of motion. And this will lead into waves. And so what we're going to find out is that we have an equilibrium position. An equilibrium position is going to be that position at which there is no force on the mass. The spring is extended to its normal length. It's not compressed or stretched. And if it's not compressed or stretched, it's not going to exert a force on the mass. Okay? And that's at the zero position. And then we say that it's displaced a certain position away from the equilibrium. Okay? Now, we remember that the spring constant has a value of so many newtons per meter. It takes this many newtons to compress it this many meters. And we're going to say that the mass of this particular spring is 5 kilograms. Okay, so that's the model for our oscillation. So if the excursion through the complete path takes a constant amount of time, the motion is stated to be periodic. Every 2 seconds, I complete this motion. Every 7.4 seconds, I complete this motion. It has a period. Remember, a period is given by the letter T, and it's the number of seconds per, and when we talked about circular motion, it was the number of seconds per revolution, but here it's just going to be the number of seconds per oscillation. So there's the equilibrium position. Okay. If the mass is displaced to either side of the equilibrium, the spring exerts a force attempting to restore equilibrium. And we call this the restoring force. So if I compress it, the spring tries to restore equilibrium. If I stretch it, the spring tries to restore equilibrium. And we will only consider the situation where the restoring force is directly proportional to the displacement. And we know this already. We know that the force is equal to however far it's displaced times the number of the value of the spring constant. Why do we have the negative sign there? What does that indicate that the spring is trying to do?
Slow down.
Move in the opposite direction.
Or bring it back to equilibrium, right? So it doesn't really matter which side of equilibrium I'm on. It's going to say that the force is either being restoring towards that way, or it's going to be pushing towards that way, because if I have a negative x and a negative k, it's going to be pushing towards the equilibrium, or if I'm pulling it back, it's going to be in the negative direction, pulling it back towards the equilibrium. So the negative sign makes it so that that force is always a restoring force. It's always pushing it or pulling it towards the equilibrium. Okay? We call the equilibrium position 0. Okay? The negative sign means force in the opposite direction to displacement. And this is basically Hooke's law. Remember Hooke's law, and this is valid only in the elastic region of the spring. We will have to do a couple of labs related to this in order to make sure that we're ready for the lab portion of the AP test, because it's likely this year that it's going to involve some kind of a spring.
What's Hooke's law?
What's Hooke's law?
Like review.
Force equals kx.
Oh, well then, never mind. I thought it was something way more complicated.
Okay? This also works for other elastic substances. These things, okay, rubber bands, anything that's got an elastic nature to it. And we know that the K is called the spring constant. We can view this from an external force perspective. What's the force required to stretch the spring? Remember that the restoring force has a negative sign, but if here's the equilibrium and we've got the spring here, the restoring force is negative, it's going that way, but the pulling force or the extension force is going to be a positive value. Now, in general, the signs aren't going to make a lot of difference, but occasionally you can get confused if you don't keep them straight. So, the anatomy of an oscillation, you've already got a fair amount of this. The number of units of separation between the mass and the equilibrium position at any point is going to be the position, and the position, the number of units of separation, and I've given you the position of all of these different things here in the diagram. A cycle is one complete back and forth excursion. Okay? From wherever it starts to here, back to here, back to here would be one cycle. Okay? So from wherever it starts back to its original point, not here, but after it completes its excursion to the entire thing. So the excursion here would be there and so on. Okay, so that's a cycle. Period, you're familiar with, time to complete one cycle. Amplitude is going to be the maximum displacement from the equilibrium point. And this is going to be a little bit more annoying to try to get used to. The amplitude is either +6 here or -6, and it's the maximum point which the object reaches. But it's going to come into a lot of our calculations, and it's going to be, for some reason, I'm not sure why, it seems to be hard to remember just exactly what that represents. And then the frequency is the number of complete cycles per second, and we remember that it is the reciprocal of the period. So frequency is 1 over period, period is 1 over frequency. So when we have this excursion, or we have this cycle, no matter where it's at in the cycle, except at equilibrium, the restoring force is always acting on this. And the restoring force is always accelerating the mass toward the equilibrium point. Now, we'll find out that this could be modified by other things, friction or gravity especially. Usually they won't put friction in a spring oscillation type of thing, but they can, and we'll see examples of it. But normally we have the force accelerating the mass towards the equilibrium point, and the force is going to be the greatest at the maximum displacement, right? So if I have my equilibrium here and my maximum displacement, it should make sense that when the mass gets to this point, that's the point at which the spring is going to be the strongest, right? It's going to have its greatest force there or at the other side. So the force is always going to be the greatest at the maximum displacement. It's going to be 0 at the equilibrium point. And so you might be asking, well, wait a minute, if there's no force in either direction at the equilibrium point, how does it ever get past the equilibrium point? And what's your response to that? Yeah, it just stops in the middle, right? No, it doesn't just stop in the middle.
Momentum.
It's momentum carries it past, right? It's momentum carries it past, because what's the velocity going to be at the equilibrium point?
The highest velocity.
It's greatest, right? At the equilibrium point, it's going to have its greatest momentum. That's where it's going to be going its greatest. And then as it snakes past the equilibrium point, the restoring force grabs onto it and starts to slow it down. But as the force is the greatest at the end, where is the acceleration going to be the greatest? At the ends. But its velocity at the ends is going to be 0. So we have this weird situation here where we have no force, but we have the highest velocity, okay? And at the ends, we have the greatest acceleration, but no velocity. Okay, so it's kind of weird and a little unsettling. Okay, so because of the negative sign in Hooke's law, the direction of the restoring force in the mathematical situations will always be toward equilibrium, and you can trust that. Okay, so at this point here, I've got a restoring force, and it's going to be kx, right? If I know that kx is my restoring force, if my x is 4 meters or negative 4 meters, my restoring force is going to be 20 newtons. 20 newtons toward the equilibrium point. When I get to 2 meters, 5 newtons per meter times negative 2 meters, my force there is going to be 10 newtons. And then here the force is going to be 0 newtons. And as we go back the other direction, I'm going to have a negative force pulling it back. And so its momentum is going to carry it further and further until the restoring force reaches its greatest point and begins to accelerate it in the other direction.